I'm sorry?
Would a JPEG or a PNG be acceptable?
I would think so.
All right, in the submission, you said that you wanted a PNG.
I can't hear you.
Or in the submission, you said you wanted a PDF.
PDF is definitely preferable, but just because it's an online submission quiz, a PDF, I mean, a JPEG would be fine.
I tell you what, take the picture, upload it, but just in case, pass all the quizzes to the center of the room and forward. Okay, just in case if there's some hiccup, we can still grade. Yeah, make sure your name is on it. Yeah, it's the first time we've done this, there may be some hiccup, but we'll have a backup plan. Yeah, and pass it forward to the center of the room and forward to Mike, where he's sitting in the front. Yeah, pass it forward. All the way. Yeah, that being the case, in the future, you can upload it maybe at the end of the class, just to save some time. Yeah. But it's easier to deal with paper copies that will be returned to you separately. All right, so are we all done? So I want to revisit the continuity equations. This rather intimidating looking continuity equation is what we ended up with last time. The simplest version of this, just to remind ourselves, and we don't get panicked by seeing a lot of vector and integral and so forth. The more practical continuity equation is simply rho VA. You use that to solve many problems, but now I do a deep dive just to explain to you how this form of the continuity equation comes about, and that's where the Reynolds equation comes in. And then after I've done with that, then next time I can actually take a big jump to show you how the momentum equation comes about, also by way of the Reynolds transport theorem. So the objective now is to show you how we arrive at that equation of most general formulation of continuity. There's no assumption. It's steady as well as unsteady. If it's steady, the first term disappears. Right? If it's unsteady, like your homework problem, then I have to deal with it and account for time-changing events, like that air compressor in the tank. It's also general in that I make no assumption about the density. It can be constant, which is what we call incompressible, or it can be changing density, what we call compressible. And that's the problem you have work on the jet engine, where fuel is added, air get pulled in, and combustion product spill out of the tail. So it's as general as you can get. I can use this to solve any complex problem like the jet engine out in Asia. The origin of that is credited to a British gentleman by the name of Reynolds. Have you heard this name before? Where? Reynolds number in Python. And he's the same gentleman to give us the Reynolds number. So what this is, taking a system equation and able to convert that to a control volume formulation. So what's the system equation for continuity that we started way back in the first lecture? What's that called? Conservation of what? Of mass. Yeah, very simple equation. And this formulation allowed me to take that and do some song and dance. And I settle, that equation will come out. So to do that, I have to remind you of the homework, where we have a T where on the left side I have two streams of fluid, could be air, could be water, coming towards this fluid device. And the shaded area simply represent the chunk of mass in the system that enter and leave my control wall. So this simple cartoon that you have worked on way back, where I'm bookkeeping the quantity of something, if its continuity is mass, going into my control wall, as well as the same quantity leaving on my control wall. If it's continuity, then it's the mass leaving my control wall. By tracking that and go through a lot of algebra, I will be able to develop a general equation where first definition of nomenclature. At first glance, this is very abstract. So capital B is just any property of the fluid, which we will have some example momentarily. Beta is the same quantity except per unit mass. And we'll see by example what some of those may be. So now speaking as a mechanical engineer, what are some of the equations or system analysis, or what kind of quantity of this capital B that may be of interest to you? The very first one is trivial. Continuity. So what do you think that capital B is? Mass? What other quantity of interest to you as a mechanical engineer? Huh? What are we dealing with in the second part of this chapter 5? Force and momentum. Momentum, very good. What else will be of interest to you as a mechanical engineer that would spend the next second half of the semester doing a deep dive? No? How about energy? Right? First law. Studying that right now. And last but not least, in some turbo machinery type application, we can also look at angular momentum, torque, how it changed. So those are the key quantity or equations that you have looked at in the past in system analysis, conservation of mass,